All right, let's dive right into this explainer. Today, we're exploring the invisible, kinetic energy that surrounds us every single day. It shapes how we experience the world, how we communicate, and even how we enjoy our favorite music. We are talking about the physics of sound. It's a phenomenon so constant that we honestly just take it for granted. But the mechanics behind what your ears are actually processing right now, absolutely fascinating. Actually, let's start with a really quick physical experiment. Right now, gently put your fingers on the front of your throat, right over your voice box, and just hum a low note. Do you feel that buzzing against your fingertips? That is the literal, physical vibration of your vocal cords. You're not just making a sound, you're creating actual kinetic movement inside your own body. Section 1. The origin of sound. How exactly does sound begin? Well, here's the absolute fundamental rule of audio physics. Every single sound you've ever heard in your entire life begins with a physical movement, specifically a vibration. A vibration is just a quick back and forth movement. Think of plucking a guitar string. When you pull that string and let it go, you can actually see it blurring, right? It shakes back and forth super rapidly. But that string isn't just moving in isolation. As it violently shakes, it acts almost like a tiny paddle, physically pushing and shoving the invisible air molecules right next to it. And when those air molecules get shoved by the guitar string, they immediately bump into the air molecules next to them, which bump into the ones next to them, and so on. It creates a domino effect. Think of dropping a pebble into a totally still pond and watching the ripples expand outward. The water itself isn't flowing from the center to the edge. Instead, the energy is being passed along. In the exact same way, the air molecules right next to the guitar don't travel across the room into your ear. They just bump their neighbors, transferring the sound energy outward in this ever-expanding sphere. So that traveling energy? That's what we call a sound wave. It's a vibration carrying sound energy from one place to another. These invisible sound waves are constantly washing over you, and when they travel right into your ear canal, they strike tiny, delicate parts inside your inner ear. They actually cause those parts to vibrate in the exact same pattern as the original guitar string. Your ear instantly translates those microscopic physical vibrations into electrical signals, shoots them to your brain, and your brain says, "Ah, okay, that's a guitar." But sound waves can't just exist anywhere. That brings us to section 2. Through a medium. How sound travels. Since sound is entirely reliant on molecules bumping into one another, it simply cannot travel through empty space. It absolutely requires an environment. Scientists call the material that sound travels through a medium. Now, this medium can be a gas, a liquid, or a solid. For us, walking around on Earth every day, the most common medium is just the air we breathe, but it's not the only one. Have you ever been underwater in a swimming pool and heard someone clinking rocks together? Sound actually travels remarkably well through water. In fact, whales sing to each other across hundreds of kilometers of ocean using water as their medium, and it travels through solids too. If you press your ear flat against a wooden desk and have a friend gently tap the far end, you'll hear that tap loud and clear right through the solid wood. So on Earth, we are totally surrounded by abundant mediums, air, water, solids, giving sound waves plenty of molecules to bump into. But outer space is completely different. Space is a near-perfect vacuum. There's almost no air, no matter, and therefore no medium. Because of this, astronauts floating outside the International Space Station could literally be right next to each other, but if they shout at the top of their lungs, they wouldn't hear a thing. There are 0 air molecules to carry the vibration from one mouth to the other ear. And that's exactly why they have to rely on radios, which transmit information using light waves, not sound waves. Okay, moving on to the anatomy of sound itself. Section 3, pitch versus volume. You know, people constantly mix up pitch and volume, but they are completely different things. They're governed by totally different aspects of a vibration. Pitch is determined entirely by speed, how fast an object vibrates. Volume, on the other hand, is determined by physical size, how far the object is physically swinging back and forth. Let's break that down. Let's walk through some real-world examples.
If an object is vibrating incredibly fast, it produces a high pitch, like a tiny bird chirping or a small silver bell. But if an object vibrates slowly, you get a deep, low pitch, like a giant bullfrog croaking or the rumble of thunder. So that's pitch. Now look at volume. If you take a drum and just gently tap it with your finger, the drum head barely moves, right? It creates a small vibration, which gives you a soft volume. But if you take a heavy drumstick and absolutely bang that drum as hard as you can, the drum head physically moves up and down a significant distance. That's a big vibration, which creates a loud volume. Louder sounds literally carry more kinetic energy because they start with a larger physical movement. That is exactly why a shout has enough energy to carry all the way across a noisy playground, while a gentle sigh just dissipates after a few inches.
Let's put this to the test. I want you to really think about this for a second. Is a whisper high or low? And is it loud or soft? A lot of people assume that because a whisper is soft, meaning it has a very low volume, it must also be a low pitch. But try whispering a really sharp S sound right now. It's incredibly soft, meaning the volume is low because the vibration is small. But the pitch is actually quite high, meaning those vocal cords are vibrating super fast. This brilliantly proves that volume and pitch are completely independent properties of sound. Which leads us to Section 4, the DIY Sound Lab. Let's test it yourself. I highly encourage you to set up this simple tactile instrument at home because actually feeling the physics of sound makes it so much easier to understand. All you need is an open-top box, like an empty shoebox, a pencil, and a few rubber bands of clearly different thicknesses. Just stretch the bands around the box so they cross the open space. Slide a pencil under the bands at one edge to lift them off the cardboard slightly. This acts like the bridge of a guitar and lets them vibrate freely. And just like that, you have a working acoustic instrument. When you pluck the bands, you are literally transferring kinetic energy from your fingers directly into the band, then into the air, and finally to your ears. You can systematically log your observations in a data table as you experiment. First, pluck the thinnest rubber band, then the thickest. What do you hear? Next, grab one of the bands, pull it so it stretches tighter, and pluck it again. Finally, press your finger down right in the middle of a band, pinning it to the box, and pluck just the remaining short side. Track whether the pitch goes higher or lower with each specific change. Here are the expected results of your little experiment, and they anchor perfectly back to our core rule. The thinner bands, the ones you pull tighter, or the ones you artificially make shorter by pressing your finger down on them, all of these have less mass or higher tension, which causes them to vibrate faster. And fast equals a higher pitch. Conversely, the thick, heavy bands, or the ones that are loose and long, well, they take more time to swing back and forth. They vibrate slower, and slow equals lower pitch. It's beautifully predictable physics. To really hammer home the reality of this kinetic energy, let's look at one final super powerful visual proof. If you ever get your hands on a metal tuning fork, strike it hard against a rubber surface. It'll emit a clear, ringing tone. But if you look closely at the prongs, they usually just look slightly blurry. They're vibrating far too fast for the human eye to track. However, if you take that ringing tuning fork and gently dip the tips of the prongs into a glass of still water, the water will violently splash outward. It's an absolutely amazing thing to witness. Even when the vibration is too fast to see, the physical kinetic energy held within that metal is powerful enough to explosively move water right out of its way. So sound is never just noise. It is physical motion. It's a chain reaction of molecules dancing through the air to reach you. As we wrap up this explainer, I want to leave you with this final provocative thought. Take a moment of silence right now. Look around your room and ask yourself what invisible vibrating energy is moving through the medium around you right now. Keep your ears open, keep observing, and I'll see you in the next explainer.